Having seen what the math looks like when we considered a piecewise external function with the spring mass system, we saw that the mathematics got fairly complicated fairly quickly. However, there's an important tie-in to the simulation and the prediction that it's making that is much more simple and much more intuitive. What I'm going to do is show you an animation of what that spring mass is doing as the external force is ramped up and then turned off, and then we'll play it again for a second time to allow you to capture some of the features yourself. So here's our spring and mass. What we're doing is increasing the force. You can track the time and the magnitude of the force externally here. It's going to stop at 3 seconds, and that's when we essentially let go of the mass, or we stop applying the external force. And we see that the mass bounces back towards equilibrium, and even though there are oscillations going on here, they're a very low amplitude. So this corresponds to the e to the negative at sine and cos terms that we had in our solution past time 3. Let's play that again. Notice we're pulling harder and harder and harder on the mass. That's what this green line represents. And then we let go at t equals 3, and that corresponds to the motion that we see here. This is literally the graph of the function we computed on paper. Again, we have the oscillations that are dying out fairly quickly. That's because of the heavy damping coefficient that we have, the large damping coefficient. So what I'd like to point out just as one additional feature is that if we look at the region up to time 3, we do see something almost like linear growth, and that comes from our formula. There's a 1/2 t in there. But you also see it's not a pure straight line. We have some kind of loose oscillations, and if you look at the frequency here and the frequency of the oscillations in this side, they're the same. They have to be the same because the math and the formulas are the same. What we see though is that the amplitude of the oscillations on this end are very small, so what dominates are the 1/2 t term, or is the 1/2 t term. Afterwards, we get the much more dramatic, much larger oscillations once the external force has been removed. But it's important to note and recognize that all that complicated mathematics predicts something that is reasonably intuitive. If we pull upwards on a mass like this, then it's going to follow us because we're applying a force. But then when we let go of the force, it's going to behave as if it had been displaced and then let go. And that's exactly what we see in the resulting graph.